In this work, we have investigated the MRI magic angle effect in the knee cartilage of the red kangaroo. Red kangaroo is the largest living marsupial, and it has a remarkable biomechanics. It can hop at 70 km an hour over short distances, sustain speeds of 40 km an hour, and it can cover up to 9 meters in a single leap. The knee joint is a crucial element of the kangaroo biomechanics. The ground reaction force exerted on a kangaroo knee joint is several times higher than the force experienced by a human running at an equivalent speed. The kangaroo knee has a very unusual cartilage makeup. In most mammals, the knee joint is lined solely by hyaline cartilage, but the tibial plateau in the kangaroo knee contains two different types of cartilage: hyaline articular cartilage based on type 2 collagen, and fiber cartilage which is based on type 1 collagen. Fiber cartilage lines the center of the tibial plateau, while hyaline cartilage lines its periphery. This is a unique feature of kangaroo knee. The two types of cartilage have different biomechanical properties. It is these two types of knee cartilage that we studied using the MRI magic angle effect. The magic angle effect is the dependence of the transverse relaxation rate of water protons on the orientation of the tissue relative to the static magnetic field. It is a well-known feature in MRI of aligned collagenous tissues. These are 6 images of the same bone cartilage plug from a bovine patella that has been imaged at 6 different orientations. As the sample orientation is changed, the dark and bright bands within the layer of cartilage appear or disappear. This is because the transverse relaxation rate at different depths depends differently on the sample orientation. The relaxation rate constant is the sum of the isotropic component, which depends only on the chemical makeup of the tissue, and the anisotropic component, which depends on the degree of alignment of collagen fibers and on the angle of alignment relative to B0. We can quantify this behavior by constructing a depth profile of the transverse relaxation rate at each sample orientation. The anisotropic component of R2 can be estimated as the difference between the R2 at the 0 degree and the magic angle orientations. In this plot, the regions where the R2 at the 2 sample orientations is the same correspond to the regions of no preferred collagen alignment, known as the transitional zone. The regions where the R2 differs between the 0 degree and the 55 degree orientations correspond to the superficial zone and the radial zone, in each of which collagen fibers are relatively strongly aligned. This slide shows the depth profiles of the transverse spin relaxation rate constant in different types of kangaroo knee cartilage. We have measured both femoral and tibial hyaline cartilage, as well as tibial fiber cartilage. 3 samples of each cartilage type were measured, and this slide shows the average profiles for each type. For each sample, we have mapped the R2 when the sample was oriented perpendicular and at the magic angle to B0. These 2 depth profiles are shown in the left panel of each pair of plots. The right panel is the profile of the anisotropic component of R2, which was calculated as the difference between the left 2 plots. That profile probes the degree of collagen alignment at a given depth and therefore reveals the zonal structure of the cartilage. All 3 types of cartilage showed the presence of the superficial, transitional, and the radial zones. However, the relative thicknesses of these zones varied significantly between the different types of cartilage, as did the apparent degree of collagen fiber alignment. We discussed these findings in light of the biomechanics of kangaroo knee. Different cartilage types also differed in how the R2 profiles behave near the bone. In hyaline cartilage, the anisotropic component of R2 exhibited a drop very near the bone, but in fiber cartilage it did not. Also, the magic angle R2 profile of the fiber cartilage exhibited a rapid increase very near the bone. This is consistent with a relatively high proteoglycan content in the bottom 5 to 10% of the tibial fiber cartilage. We call this the attachment subzone and discuss its significance in the paper. In particular, we hypothesized that this feature can be useful for non-invasively distinguishing between hyaline cartilage and fiber cartilage in regenerative therapy treatments.